Good evening from Turkey. My name is Melike Çınar. I am the moderator of this keynote session, also one of the volunteer organization team member. Mr. Khaled Mahmoud is the Chief Bridge Engineer for Bridge Technology Consulting and our first keynote speaker. Hello, Mr. Khaled. Can you hear me? Sorry, I can't hear you.
We can hear you.
Hello?
Hello. Yes, I
Hi,
can hear you.
How are you? Thank you very much for the intro.
Nice to see you, Mr. Khaled.
Nice to see you too. Thank you. Hello, everyone. It's a pleasure to be here, and I'd like to start by thanking Professor Çınar for inviting me to share this presentation with you. Okay. Can you see the presentation, Melike?
No, not yet.
Oh, okay. How about now?
Yeah, I can right now.
All right, terrific. All right, so today I'd like to speak about the some issues of the design for maintenance and longevity of long-span suspension bridges. And as we all know, we have been pushing the envelope in terms of span length. We have a tremendous evolution since the construction of the Brooklyn Bridge in 1883 up to Akashi, and soon to be the longest suspension bridge in the world, the 1915 Çanakkale Bridge in Turkey. So this is a quick outline of what I'd like to discuss in terms of the evolution of the wire strength and the modern suspension bridge technology with the prefabricated parallel wire strands, PPWS, and the orthotropic deck, and the issues of fatigue and fracture, and also the aerodynamics and vibration issues with vortex-induced vibration. If we get a chance, we'll talk about ship collision. That's a topic of great importance when we have the main towers of suspension bridges in the water, subject to the risk of ship collision. Here's the beautiful Brooklyn Bridge that was opened to traffic in 1883 with a span length of 486 meters. And 20 years later, in 1903, with only 1.7 meter of increase was the Williamsburg Bridge. But when we start looking at the wire strength, we'll see some significant increase in the wire strength in these 20 years. Of course, the first introduction of the high-strength steel wire that we use today with some modification was introduced by John Roebling. Of course, the John Roebling is the master bridge builder and bridge designer that designed the Brooklyn Bridge. Moving forward about to 1964, with the opening of the Verrazano Bridge with almost 1,300 meters main span, that's here in New York City. You find that we had about 4,260 feet, or that 1,300 meters. It's a leap of increase, almost more than 2.5 times the span length of the Brooklyn Bridge. But we will see that when we get to the wire strength chart that I'm going to show in a minute, that there has been consistent incremental increase up until the construction of the Akashi, that had a leap of increase in span length and also in the wire strength. The Akashi is 1991 meters main span, and the tower height, steel tower of 283 meters. That will, of course, was a great achievement. It was the longest suspension, longest suspension bridge since 1998, and that would be rivaled very soon with the opening of Çanakkale. Also the wonderful third Bosphorus bridge across the Bosphorus with 1408. This is the widest suspension bridge in the world and has a tower height of 322 meters. That's a concrete tower, and yet to be opened in 2023, the Çanakkale Bridge with the wowing 2,023 meter main span and a steel tower height of 318 meters. I talked about the PBWS. So what was prior to or before the PBWS, all the suspension bridges like the Verrazano, like the Williamsburg, all these traditional suspension bridges were built with the spinning technology, and the introduction of the PBWS has assisted in pushing the envelope and the span length. And this is the PBWS coil being prepped for transportation to the bridge site. And here's some inspection of the strand, and you can see the socket over here is wrapped, and we inspected all that before you ship it to the bridge site. If you look at this chart, you see that we're starting with the Brooklyn Bridge. We have about 1,100 megapascal. That is the ultimate strength of the wire. With the construction of the Williamsburg, that jumped to 1,531 megapascal. And then from that point onwards, including the Verrazano, the Fourth Road, the Triborough, the Golden Gate, and even the store built that was built in 1998, you find the increases are not that significant. It's actually dancing around the 220, 224, with a slight increase at the Triborough and Golden Gate. Golden Gate was at 235. The significant increase happened with the Akashi. I mixed here the KSI, so my apology. Let me stick to the megapascal. So for the Golden Gate, it went up to 1620 megapascal. For the Akashi, it jumped to 1800 megapascal. And then when we constructed the third Bosphorus, we used the 1860 for the main suspension cables. And for the stay cables of the third Bosphorus, we used 1960 megapascal. There are suspension bridges that are being built today that are using 1960 megapascal for the main span wire, for the main cable wire. Okay, there are certain issues that we need to wrestle with in terms of the chemical composition and why those are important and how significant they are in terms of maintenance and longevity. You will not find this in any specification, unfortunately, neither in AASHTO nor in the Eurocode. It is all fair game. It is in the hand of the wire fabricators, and the way they do their wire has a lot to do with their own technology. Some of it or most of it is proprietary, but we will note that we get that awesome strength of the wire by increasing the carbon content and the silicon content. Let me share with you here just some mill certificates that shows that this wire with the 1960 megapascal as a specification, and you get what I consider awesome elongation capacity of 7%. If you look at the same fabricators, same wire, same bridge, same everything, 1960, and you get 4.6. That's an order of magnitude in elongation capacity. And what matters here is, or the difference comes about the change in the chemical composition. You see that the carbon content and the silicon content are higher for the wire that has lower or reduced capacity of elongation. What does that mean? Why is that important? That's important because they have these chemical compositions have a lot to do with how the wires break. But do wire break out of, or do wires break out of the blue? The answer is no. We haven't seen, and thousands of broken wires we have looked at collectively over the years, too many years, much longer than I like to admit to, but the wires crack first and then they suffer the break. Look at this bridge wire. It's over 80 years old. That's a broken wire in service. And what you see here is a crack that starts at the edge of the wire, then propagates in the cross section, then the wire starts splitting along the longitudinal axis of the wire. That is the direction of the elongation of the grains, and then it gets broken here at this rugged surface. So corrosion, well, this is corrosion. What you see on the screen now is corrosion, because you have perforation, and by definition, the word corrosion means loss of mass, anode and cathode, and the corrosion cell, and we know that from early on. But when you look at the wire, what corrosion? There is no corrosion to speak of here. What's happening here is embrittlement. Embrittlement that caused the crack propagation, and further the crack till it reaches a critical crack depth, and then the wire breaks. There are too many examples. You will not find a broken wire that does not demonstrate this form of break in one way or another. This is a brittle break. This yet another example of a brittle break, where you see the crack starting here, and again, this what we call stepped fracture. So what happens is you have the edge crack starting here and the further crack propagation. Why is this important? This is extremely important because it gives us insights on how to maintain suspension cables and how to maintain their service for much longer time at a reduced cost. It is a very expensive proposal to replace a bridge cable. This has happened few times. It happened here in our country about 15 years ago with the Waldo Hancock suspension bridge, where the entire bridge was replaced. Actually, it happened in France with the Aquitaine bridge, and Tancarville, where the suspension cables have been replaced. Here's just a schematic of the model of a crack, where you start having the crack starting very early at the edge, and then start propagating up until it reaches critical depth. Now, let's look at how this comes about, and the ramification of that to our knowledge about maintenance, and how to enhance the longevity and improve the performance of suspension cables. Well, basically what we do is we have a rod material that's about almost 1300 megapascal in strength, and about 14 to 15% elongation capacity, or the ultimate elongation. And you start successive cold drawing through dies up until you draw the final about 5 millimeter diameter. That gets you that awesome strength of, this is an old stress strain curve, but you get the awesome strength of about 1960 megapascal, but that's at the expense of what? At the expense of ductility. So remember, I said that the rod material had 1300 or about 1300 megapascal, and with the successive cold drawing, you're elongating the grains and imparting that great strength, reaching to 1960 megapascal. Actually, it reads more than that. It exceeds 2000 megapascal. And then you find out that the elongation that you started with of about 13–14% reduced to what we've seen on some of these mill certificate of about 4.5, 4.6. So you get that awesome strength at the expense of ductility. There is another toll to pay, which is increasing the vulnerability of that bridge wire. This is the nature of the beast, ladies and gentlemen. This is actually something that we know that walking in, but to span almost 2,000 meters, exceed 2,000 meters or we don't we don't resort to a lower capacity. We know that. So this is kind of knowledge we walk into with in building these long spans. But the vulnerability to hydrogen embrittlement comes about the distance between the grains gets increased when you elongate the grains, and that introduces atomic hydrogen. And then you have that triode of tensile stress, hydrogen source, that's internal environment of the cable, and actually you get hydrogen in the lattice of the wire material during the galvanization of the wire. And then you have the material condition that is the root cause, and then you have the hydrogen-induced cracking, or what we call hydrogen embrittlement. So that susceptible material coupled with the source of hydrogen and the high tensile load, and you end up with the embrittlement. Just to enumerate this, if you look at a wire that is healthy, and only engineers will call this a beautiful picture of a cup and cone. This is a textbook of a cup and cone ductile fracture of a bridge wire. You can see here, it's very distinct, very exhibitive of a ductile fracture. And you see a tremendous area under the stress strain curve that actually represents the energy that it takes to break the wire. This wire doesn't have any crack in the fracture. This wire looks very good. It looks without any section loss. It has the full 5 millimeter diameter, but just to save time and not to go back and forth, I'd like to bring your attention to the crack lurking right there. This is a crack in the wire, and that's where the wire break has taken place. And you look at the stress strain curve. Now you can appreciate what kind of damage the embrittlement induces on the wire. If you put the two curves together, you can, of course, find out how damaging the embrittlement is and how to deal with that further. Again, this comes about, you have the H2O, here's a hydrosulfide, here's the iron, and you have on the right side of the equation the diffusible atomic hydrogen that causes the embrittlement and causes the furthering of the crack growth up until the break takes place. So now, how important is this for longevity and how to equip ourselves with ways and means to elongate the service life of bridge cables? It is commonplace that we open bridge cables, older bridge cables, and unwrap them and wedge them, as you see here, what's known as internal inspection. We take samples, we test the samples, and we determine the strength evaluation. If you read on our CV, we invented the BTC method for cable strength evaluation that is being applied all over the world, here in North America, in the United States, in Canada. We applied it in Europe, and it is quite an involved task to determine the strength of an existing cable and to forecast the service life. Following the inspection and the assembling and the whole thing, we need to compact the cables back to their original diameter. What you see here is at the far end, where these gentlemen are working. This is the green metal here with the yellow pistons. This is the compactor that's being used to basically bring the cable back into circular shape. And what you see here are straps, the steel straps that are tightened with bolts to maintain the diameter of the cable up until we start the wrapping process. So here is the wrapper, here is the wrapping machine. And before we do that, before we apply the wrapping wire that's applied with the tension, pre-stress and tension, you will notice one thing. Let me show you this quick video. You'll notice here that we are using a paste material. This paste material goes a long way in providing a moisture barrier and providing basically minimize the effect of moisture. on the bridge, damaging the bridge cable. So you apply this and you see the wrapping wire coming very close. The laps are very close to each other. And then afterwards, you will see a picture of the entire cable after the wrapping. Here is the end of the panel. This is the entire length of the opened cable being wrapped with that base material. This base material goes a long way in protecting the cable. You see, we are doing a lot of things to protect the main cable wire. The main cable wire is these wires, basically, what you see here, these longitudinal element. The reddish color here is the lead paste that we don't use anymore. And there are different materials that are more environmentally acceptable and doesn't cause health issues like the lead has done. And after that, we apply the cable guards, and there is dehumidification system. But let me spend a minute here on dehumidification because if you ask me, I think the jury is still out on the efficacy of dehumidification. There are certain recent evidence that shows that dehumidification is not really doing what it promises to do. Case in point, if you look at the concept of dehumidification, it revolves around corrosion. And this is without bringing the old curve that Professor Vernon developed in the 1926 to 1928, where he took a piece of iron in an environment saturated with sulfuric acid with a certain 0.1% concentration, and he drew a correlation between the relative humidity and the loss of mass. But some time ago, people adopted that for the bridge wire. Actually, my problem with this concept or this curve is, what is the rate of corrosion? What is that? What is the units of that? You notice that the x-axis is giving us the relative humidity and percentage, which is fine and wonderful. But what is that rate of corrosion for the bridge wire? There's no typo here. It's not missing. It's nothing. It's missing because it does not exist. What matters at the end of the day is how much hydrogen will be contained in the bridge cable environment. And what are, if you look at the metrics of bridge wire degradation, in our view, it is broken wires and cracked wires. If we have less of those, that's a good sign. That's a positive sign for the bridge cable. If not, then there is something to contemplate and something to study there. So in all, you don't want to have this kind of image when you open your bridge cables in a few years, regardless how old the cable is. Is it 30 years, 50 years, 80 years? Whenever the first opening of a cable should not look like this, which is not a total disaster. Of course, we fix all these wires, we splice them, and we provide tension back in them, and we move forward. But the issue is, if you have too many of these, and if you have cracked wires that yet to be to break, that will of course impact the longevity issue and will reduce the service life. All these broken wires had brittle fractures, and they had no cross-sectional loss, and it was an emphasis placed on the brittleness of those fractures. Okay, I'll skip this part about the, if we have time, I'll get back to our work on Chacao. We presented some interesting cable solution at the center tower. I can talk to you about it later on if you wish, of course. One of the other advances that we have been, it's commonplace now that we use orthotropic deck design for the suspension bridges, because it reduces the weight on the cables. That makes the cable smaller, of course, and that's a desirable thing I, for one, wouldn't like myself and my staff to start looking at a cable diameter of 10 feet. That would be a bit daunting, a daunting task. So the orthotropic deck presents a reasonable solution to reduce the weight of the bridge, but it comes at certain toll as well. We have, you see, when we advance our technology, we have to really look back and cover our tracks. What is missing and what is going to give in, and what are the vulnerabilities? Over here, you see these are U-ribs at the top, and there's a thin steel plate, and here at the bottom of the bridge deck, you see the U-ribs with the deck plate on top, and this is a cross beam. Cracks can develop either in the deck plate itself, can develop in the longitudinal weld between the rib and the deck plate. They can develop at the splices where you connect the U-ribs, or they can develop at the connection of the U-rib to the cross beam. So basically, here's the kind of crack that develops in the deck plate, and you can see here the cross section. And what we do is we do testing. Almost all the jobs that we have been involved with the orthotropic deck for a suspension bridge, we have been doing testing, and you do the testing to qualify the welding technology that is automated and find the heat input and many other parameters. The technology is wonderful, but what we need to do is to qualify this technology that it does not cause what's known as melt through. The melt through is basically causing a crack-like defect, like what you see here circled with the with that red color, and you see that will start a fatigue crack here that would tremendously reduce the fatigue life of the bridge deck. Over here is another sample that we tested on a bridge, a suspension bridge, where you have no melt through, and that was done with a setting of fatigue actuators and all instrumented to find out how many cycles and to find out when the crack initiated and how far it propagates and how many cycles and the whole 9 yards of this. So another thing that ought to be used, not only the UT techniques, but also X-ray. The UT, the ultrasonic testing techniques, is proper for planar kind of discontinuity, but the UT is less suitable in detecting porosity in the weld. And that's why the X-ray is a lot better technology to detect the porosity in the weld that can cause fatigue and that can cause cracks. And that, of course, is a very unpleasant situation. I can imagine the footage or the square meters of a bridge deck that suffers from this kind of cracks. It becomes a very, very, very troubling issue. These fatigue failures, if it happens, where part of the bridge deck start giving into to these cracks, or can lead to closures, neither of which is a desirable or speak of longevity and good maintenance. Now, I'd like to show, probably I don't think of any civil engineer that haven't seen this Tacoma Narrows video.
Collapse of all time. In July of
it's always good to remember this kind of catastrophe to avoid them.
The peninsula with the Washington State mainland was officially dedicated and open for use. But from the very beginning, its actions were more than peculiar. The bridge actually swayed and undulated like a huge snake. So much so, the locals called it Galloping Gertie. At 11:08 a.m. on the morning of November 7th, 1940, a professor of engineering happened to be on hand to film the behavior of the bridge in the hope of determining what structural fault might be causing its wild and woolly movements. These are the startling films that he was fortunate to shoot. The bridge buckled and finally gave way with a roar. Its midsection tumbled into the sound 190 feet below.
Well, if that doesn't break your heart, I don't know what would. But going on, this happened in 1940, so you would think that that's something of the past. It will never happen. We know better. We can model anything on the face of the earth, and we figured out all the phenomena, didn't we? But up until probably close to 60 years on, 1998 construction, without mentioning the name of a bridge, but let's look at this. It is the same kind of vortex-induced vibration that's happening up until almost today on a major suspension bridge that was recent construction. And you see the hangars hate bending. We don't design to have hangars to have bending, but you can see how much bending happening on these hangars and the ramification of that. Of course, this is a serious issue. The vortex-induced vibration is a peculiar phenomenon, and we need to have a better grasp on this to avoid this kind of problems. Probably the last topic I'd like to talk about today is the design against ship impacts or ship collision. There is the Voisin formula has been known. Voisin's formula has been known since the mid of the 20th century, which basically determines the equivalent static force caused by the impact as a function of the dead weight and tonnage of the ship and the ship impact velocity in knots. So you can have these kind of graphs. They are readily available, and you can determine what kind of ship impact that the Voisin's formula would produce. But what is missing about this concept is the energy that would be absorbed by the tower structure and how to mitigate that. So in a nutshell, we can talk about, we'll see some slides further of this, how to deal with that. Just build something around the bridge tower. If you have shallow water, if the water is shallow enough and it is economically and it is economically feasible to do that, that's a good question. Had this happened before? Yes, it had in our country. Unfortunately, about a little over 40 years now, with the Sunshine Skyway collapse with a 20,000 ton vessel that hit this rather good-looking bridge in 1980. That's the morning of May 9, but later on, that's how the bridge looked like, and it's just absolutely horrible. I took the liberty of getting this video to show you. It is actually from the morning of
is Pulse 13's Neil
the
Vicino
collapse.
to tell us what he sees from there. As you've probably already heard from Tom Martino and Tim Smith, the weather is deteriorating out here rather quickly. We're going to try and tell you, as far as we know, from what we can see and what we've been told, what did happen out here at 7:39 this morning. We're aboard Captain Jack Nowling's 23-foot Mako, and we're less than, about 40 or 50 feet just to the west of the Summit Venture, the ship that hit the Skyway Bridge this morning. She's a 606-foot ship out of Liberia, out of Monrovia. She is a phosphate carrier. However, we told she was not carrying phosphate when she was inbound this morning and hit the bridge. These incredible pictures I'm sure you're seeing right now are, of course, of the ship and a large part of the superstructure from the skyway, maybe 40, 50, or 60 feet, sitting on the bow of the Summit Venture. And the Summit Venture is less than 1,000 yards away from what is left of the Skyway Bridge. As photographer Jewel McGee is probably showing you now, you can see where the span was cut off. There's still some debris hanging from there. We're told that right under that spot, just a little bit north of where the debris is hanging, they are not searching there because they're afraid of the support. They don't know what type of support. I understand there's hardly any support there, and so the search operation is not taking place underneath there. But the divers are diving the rest of the length. I understand it's about 1,000 feet of the bridge that was taken out. They're searching there, of course, for any more bodies, and I suppose at this time probably no chance of survivors.
Mr. Khaled,
Yes.
it is really heartbreaking, and also you have 4 minutes.
That's exactly what I need, Malika. Another 4 minutes. Perfect. So what we done, peer protection, this is an image of, what we done something along these lines at the Bordeaux Lift Bridge in France, that Jean-Jacques Delmont Bridge in Bordeaux, where we built a peer protection system around it. The water was shallow enough to allow us to do that. But in deep water, here is a shallow enough that we done this kind of fender system. But in deep water, what we thought of and what's been done is to have a floating fender system in which you have a system of actuators and damping devices, dampers, components here, that will be hugging the tower structure, and it provides this kind of attenuator in case of a ship impact. That will definitely be a very good thing to do. Well, in conclusion, of course, this is a very large topic, long span bridges, long span suspension bridges, or all cable supported bridges for that matter. We don't have any special specifications for that. I can speak for AASHTO. I sit on some committees with the Federal Highway Administration. We developed some guidelines for long span bridges, but nevertheless, there is no particular document that we can go to as here in America or our friends in Europe that puts together a set of specification that's much needed to have this kind of guidelines and standards for long suspension bridges, which are by definition complex structures. And the operating environment is unforgiving, as we all know. So longer suspension bridges require planned preventive maintenance, and that goes a long way in providing the good performance and the longevity that these bridges need. With this, I conclude my presentation. I thank you very much for listening. And I leave you with this picture of stability, longevity, and great shape of the Brooklyn Bridge that is coming up on 140 years come year 2023. Thank you very much for listening.
Thank you so much, Mr. Khaled. Dear participants, do you have any question to Mr. Khaled? I think they don't have any question. Mr. Khaled, thank you so much.
Thank you.
That's an amazing presentation.
Thank you, Malika. I appreciate it.
Next and last keynote speaker is Mr. Hany El Naggar. Hello. Mr. El Naggar, can you hear me? Hello, Mr. El Naggar.
Oh, hello. Hi.
Hello.
Hello, hi.
The last keynote speaker is Mr. Hany El Naggar, is a professor from Dalhousie University. And Mr. El Naggar, if you're ready, you can start.
Thank you so much. I sent you my presentation recording yesterday, and you did receive it.
Right now, I can't see it.
I sent it yesterday. Professor Fulak sent me email that you received it.
Okay, okay.
Yep.
Can you wait a minute, please?
Sure, sure. I sent you another link.
Mr. El Naggar, can you hear me?
Yes. I sent you another link.
Yes, yes. We have your video, but I didn't know we are gonna use it. Sorry for this. And I'm downloading it.
Yes. Thank you.
Share yapıyorum. Şu herhalde.
Right. Good afternoon, ladies and gentlemen. Thank you so much for inviting me for this conference. Today, unfortunately, will not be in person. Next year, we'll move together, our beloved city. So today, we're going to talk about the performance of integral apartment bridges in cold regions and their modeling. Okay. My name is Hany El Naggar. I'm a professor of geostructural engineering at Dalhousie University, Canada, Nova Scotia, Canada. So during our lecture today, we're going to have some kind of an introduction. Then we're going to move to the objective of this project. Then we're going to talk about the considered case study that we used in this research. Then we're going to talk about the numerical model. Then we're going to talk about the results and discussions of the numerical results and the drawn conclusions. So, integral apartment bridges in general are binary structures in which both of the superstructure and the substructure are moving together into and away from the soil. So, during summertime, when we have the expansion, okay, the apartment will going to move toward the soil. whereas during the winter time, when the concrete shrinks, we're gonna move away from the soil. So accordingly, we have this kind of cyclic nature of the. Also, integral abutment bridges, we're gonna eliminate the use of the expansion joints and bearings, which is a huge savings. So we don't need any expansion joints and bearings and stuff like this, because the whole structure is one unit. So also the simple geometry of the abutment with a single row of piles typically will gonna result also in a faster construction. The elimination of the expansion joints, as we said, and bearings, will gonna reduce significantly the construction and maintenance costs. That's why integral abutment bridges are gaining popularity and their use is on an increase. So in general, this kind of soil structure interaction is a complex soil structure interaction, basically. Why? Because during summer, as we said, the bridge we're going to expand, we're going to push on the soil, so the soil will be in its passive mode. Whereas during the winter time, the concrete will shrink, and then the abutment will going to move away from the soil, backfill soil. So this is going to constitute the case of the active earth pressure or near active earth pressure. So the soil structure interaction here involves lots of phenomena that you need really to take into account in order to have a reliable model. Okay, because it's usually, as we see, it's just moving back and forth, back and forth. All right? So in order to better understand the effects of the thermal movement of the bridge on the soil structure interaction, a two-dimensional finite element analysis was conducted using Plaxis 2D. In this lecture today, we will gonna explore the effect of the employed soil model on the predicted earth pressure within the soil mass. So usually, it's where commonly most engineers are using the Moore column failure criterion to define the soil behavior. This model is very good if we are talking about foundations, load in the vertical direction, and one cycle of loading under static loading conditions. However, when we have a load which is cyclic in nature, the Moore column will not be the best, as we're going to see later on in this lecture. So in this specific research, we considered a case study from New Brunswick here in Canada. Okay, so we have an instrumented bridge that we have the results for several years, right? And then we're gonna build our numerical model, and we're gonna validate our numerical model using the data obtained from the field test. Also, this lecture we're gonna show that the Moore column model, which is elastic perfectly plastic model, which is often used to model the soil behavior as a first order model, is not capable to accurately describe the behavior of the soil during the unloading, reloading process that happens, right? And a more advanced soil model, such as the hardening soil model, is more appropriate and is needed. So the considered case study here, which is the Industrial Park Route 7 underpass. So this is a bridge near Fredericton, New Brunswick, here in Canada, and the East Coast. So as we see here, the finite element model results were compared with the monitoring results, as we said before, of this integral abutment bridges that has 238 meters wide spans at the industrial park here, and which underpasses the New Brunswick 2004. As reported in Huntley 2009, the superstructure consists of bulk T 1800 girders, okay, below 225 millimeters of reinforced concrete deck. We have two abutments, one in the east and one in the west, with 4,300 millimeter average height, so around 4.3 meters, the height, okay? And the thickness of this apartment is 1.2 meters, okay? A single row of 12 HP 310 by 132 piles are oriented along their weak axis, okay? are used to support each of these abutments. The top 300 millimeter of the pile were installed in the 1.2 meters wide trench backfill with loosely placed sand material. So we have this kind of 3 meters. So we have this kind of loosely placed sand. So we allow the pile to move. So we are facilitating the system to be a flexible system. So it moves easily during the summer, during expansion, and then it moves easily again during the contraction when it goes back. Also, we are using a drainage layer, 1.5 meters behind the apartment here, and we are using a Poro A backfill material, properly compacted and left of 6 inches, right, in the back of the drainage layer, as we see here in the drawing. So this bridge is instrumented with over 100 different sensors, okay, at various locations. We have strain gauges, we have thermocouples to get the temperature, we have deformation meters, we have displacement monitoring, we have pressure sensors, we have everything, okay? So in this lecture here, I will gonna primarily focus on the development of a comprehensive finite element model of the east apartment. We're gonna simulate the variation of the earth pressures due to the thermal cyclic loading and unloading displacements. All right? So for each of the apartment, okay, the following system was installed. So we have 3 vibrating wire contact pressure cells that's being placed, as you see in here, at near the 1/4, near the center, the middle, and near the 3/4 from the top, okay, of the apartment heights. So 1, 2, 3. All right? Okay. Well, also we are using 2 vibrating wire deformation meters, okay, and 2 tilt meters at the 1/3 location and at the 2/3 locations, okay, to measure the displacement and the movement of this apartment. Okay, detailed laboratory and field tests for the backfilling layers were conducted. So the material itself that was used for the backfilling and the in situ material and so on was tested using different tests, direct, shear, and triaxial testing, and so on. Okay. The following figures here, I'm showing you some of the monitoring results that was obtained. So as we see, the first one here is showing us the change in the translation. So in the movement of the apartment here. So in this direction here is when you move away from the backfill. So this is the active case. And in here, down here, when you move toward the backfill, so when you are in a passive mode. So here we have the upper sensor and the lower sensor for the deformation, right, as we see it. And in green here, it's showing us the temperature the same day, okay? The same thing was collected, same set of data was collected for the change in the pressure in the back of the apartment here. So again here, this green is the change in the ambient temperature, and here is showing the readings of the upper sensor, middle sensor, and the lower pressure sensor, okay? So the 2 models that we used, first is the Moore column soil model, which all of you know it. It's just the basic bilinear approximation, okay, which is a linear, elastic, perfectly plastic model, as you see here. So we have a constant elastic modulus, right, up till the failure, and that's it. And after the failure, everything just plateau. Also, we use the hardening soil model from the Plaxis library, okay, which is an advanced model capable of simulating the behavior of different type of soft and stiff soils. In the hardening model, the stress dependency of the stiffness is accurately described by using 3 different stiffnesses. So we have the triaxial loading stiffness, okay, which determines the magnitude of both the elastic and plastic strains. We also use the odometer loading stiffness, E odometer, which accounts for the plastic strain due to the primary compression. And also we have the EUR, which is the elastic modulus of the unloading, reloading, which represent the stiffness of the soil during the unloading. So as you see in here, let's say, in the beginning of the loading, you're going to have certain elastic modulus E, the E50, the secant elastic modulus. However, when you load, when you unload, okay, and then you load again, the stiffness of the soil will be higher definitely than the original stiffness. So our strain hardening model is capable of simulating this, okay? So you can refer to the background about the soil hardening model for background information on this. But the main feature that we can summarize out of here is that this model is capable of simulating the cyclic nature and the change in the stiffness that corresponds to this change in the stress. Okay, so this is the main feature and the main importance of this soil model. So we built two numerical models using the Plaxis 2D. The first model was utilized to study the earth pressure generated on the east apartment due to the cyclic thermal displacement using the hardening soil model for the soil purpose. The second model is similar exactly to the first one in the geometry, layout, and construction procedure, everything. However, we are using the linear elastic perfectly plastic Moore column to model the soil behavior in this model here. These models followed the same geometry, layout, and construction procedures of the full-scale apartment, and the results were compared with the field measured earth pressures due to that change in the temperature. So if we look into here and to the model here, we have our bile, our row of bile here, biles here, the H bars, which is backfilled here with some loose sand to provide kind of flexibility in the top 3 meters of the bile, right? And then here we have our drainage layer, and we have the Buru A backfill in the back of the apartment here. And we have, this is the approach slab in here, and this is our apartment, which is sitting on the this variable. So accordingly, the system is very flexible in the horizontal direction, exactly similar to the reality of the interior. So soil parameters adopted here. This is a set of parameters adopted for the hardening soil model, and this is the set of parameters adopted for the Moore column. And the concrete in the apartment was modeled as linear elastic because generally it will be in its linear elastic during that. Okay. Finite element mesh. So we use the 15 noded cubic strain triangle elements to model this problem in here. Plane strain conditions were assumed. The hyperbolic hardening soil model was used in the first model, as we said, to simulate the stress-dependent variation of the soil stiffness due to the cyclic load. Moore column failure criterion was used in the second model again, just kind of a reminder. And the lateral boundaries were placed about 3 times the width of the structure in each direction to simulate the infinite median. Also, the bottom boundary was placed 30 meters or more below the ground surface. So just to minimize the boundary effects. So the boundaries are far away from the location of interest, and accordingly, we're not gonna affect the study performance. We use the stage construction techniques, so we modeled exactly the bridge, the way the bridge was built. So we modeled everything exactly. We modeled the initial in situ stresses were installed first, and then we simulated the excavation and the second stage. Then we placed the bile platform, and then we modeled the biling, okay, with the loose sand in the trench, and then we built the apartment, right? And the apartment was built into 2 sections, so we simulated this in the 2 stages in here. And of course, between the stages, there are some sub stages as well, okay? And then we placed here the drainage layer and the backfilling in layers, 300 millimeters each, and it was compacted, right? And then we put the crushed stone layer, and then we have our approach slab, and then the load from the bridge. So the whole construction process was modeled and detailed. So the last stage, the cyclic displacement due to the effect of the thermal change on the superstructure was applied, as you see in here, okay? Based on the results obtained from the real monitoring situation. So we know that from the monitoring situation, let's say that the apartment moved, let's say 5 millimeters. So we apply the 5 millimeters here to the model, and then we see what kind of pressures we obtained. Okay? So if we look into the results of the analysis in here, so first here, I'm showing you the results of the finite element modeling, including the earth pressure distribution along the inner face of the apartment due to the thermal displacement, okay? And we compared this for 3 years of monitoring, okay? Duration of 3 years, okay? At the different locations, as we said before. So here I'm showing you the comparison between the second model, which is the finite model using the Moore column, okay, result obtained using the Moore column, and comparing these results to those of the field results. So as we see here in green, this is the field results, okay, for the first year, which is a continuous line. The purple here shows you field results for the second year, whereas the third, which is a continuous red, shows you the field results for the third year. Okay, and this is the pressure distribution here at the back of the apartment here. Okay, the ones and dotted lines here are showing the same, but obtained from the finite element analysis. So as we see, there is a difference. So the finite element analysis was not able, using the Moore column, was not able to capture the real behavior. If we look into here, we're going to find that, say, in the first year, we have an error of, let's say, 15% on average. In the second year, this error reached up, let's say, to 20 and 30, up to 30 something, 33 or 34% of error. In the third year, this was around 30%. So, of course, this is not acceptable. So we understand from here that the Moore column model cannot be used to simulate such thing, because in simple words, we have a cyclic loading, right? So accordingly, we know that the stiffness of the soil will be different. So accordingly, for example, if you compress the soil in a pot, let's say you have a plant pot. So you compress the soil with your hand in, right? So let's say the soil is gonna settle, let's say, 20 millimeters. Then if you removed your hand, if you release the load, the soil will not gonna rebound back the 20 millimeters full. It will gonna just rebound, let's say, 12 millimeters or 15 millimeters. And you're gonna end up with some permanent deformation, right? Because this is the nature of soil. However, Moore column is not equipped to simulate this. Moore column only uses one stiffness, one elastic model. So accordingly, we will not be able to simulate this. However, when we used the hardening soil model here, as we see, okay, we were able to get a very good match between the finite element results and between the predicted results. Was a maximum, let's say here, in the first year was less than 10%, less than 10%, and less than here 12% or so. So the results are much, much better. Keeping in mind, this is a 3D problem that we reduced to 2D, right? We reduced this to 2D. It's originally 3D. So right now I have a master's student who is continuing the research, who is working on the 3D modeling of this. Okay, so even this 3 and 4%, and even the 8% that the maximum here that we got can be enhanced. Okay, so we're working in this direction. So we see that the hardening soil model has some merits. Okay, and also we are right now using the hardening soil model with a small strain. So even this will gonna be much better. Hopefully, in the conference next year, I'll be able to meet you all in person and we can share the results together. So, to summarize this lecture here, so a detailed finite element analysis using PAXIS 2D were conducted to examine the manner in which the earth pressure are generated behind the integral abutment bridges due to the cyclic displacements. The conclusion of the study was, first, the simple Moore column model is not capable of simulating the soil behavior during the cyclic loading unloading, as the soil stiffness is nonlinear. Second, the hardening soil model can simulate effectively the nonlinearity of the soil behavior due to the cyclic loading, as it can simulate the stress dependency or the stress dependent variation of the stiffness with the stress level. Okay. Also, the maximum value of or magnitude of error using the hardening soil model was maximum, was 12%, was all of the results much lower than this. And actually, as we said, right now we are even working on enhancing this. Okay. The maximum value of the error using the Moore column was 34%, showing that Moore column is not the way to do this. All right. So, second phase of this project that we are currently working on is producing three-dimensional finite element modeling using the simulating the whole soil structure interaction, simulating the compaction effects, simulating everything that we are working on right now. We are also using another version of the hardening soil model, which is the hardening soil model with a small strain, which is capable of simulating the much higher stiffness of the soil at very low strain magnitudes. So this stage is currently underway, and hopefully, as I said, next year, I think the conference will be in the summer, in August, wherever. So hopefully we all meet in the beautiful city of Istanbul to share the results of this. And I'm waiting for all of your questions. Thank you so much. Thanks. Good afternoon, ladies and gentlemen. Thank you so much for inviting me for
Professor El Naggar, can you hear me? Yes, I think she's out. Yeah. No. I think Professor El Naggar is out. But do you have any question? Can you leave the chat part? Dear participant, it is the end of the first day of Istanbul Bridge Conference. Thank you so much. I hope you enjoy it. Bir şey demek istiyor musun? Dear participant, it is the end of the first day of Istanbul Bridge Conference. Thank you so much. I hope you enjoy it. Mr. Selçuk, you are laughing, I think. I can't hear you, sorry. We can't hear you.
Me now? Yeah. Can you hear me?
Yeah, yes.
Okay. So there is another Çınar. His voice is muted. So he's talk, but we can't hear whatever. First of all, thanks for this fruitful first day. It was very informative for me. And I appreciate for your readiness of this event. Hopefully next year, of course we have tomorrow, but hopefully next year we will have a face-to-face B2B seminar if the COVID-19 or 20 or 21 allow us. Thanks again. Thank you.
We thank you.
Yeah, thanks. That's good. And we'll see tomorrow.
Okay.
The Alp is still muted. Alp is still muted that we
Yes,
can't
yes.
hear.
There will be echo for some reason, I don't know. But I am the voice of Çınar. And we are inviting you to tomorrow for the second day of Istanbul Bridge Conference.
Sure.
And
sure.
I wish you all good night.
Okay. Thanks a lot again. All the best to everybody, for all participants, especially to you. Thank you. Bye-bye.
Thank you. Thank you.